The talk's title is Continuous Variable Gate Teleportation and Bosonic-Code Error Correction. That's in reference to a recent paper published towards the end of last year by myself, Ben Baragiola, Ralph Alexander, and Nick. And so the bulk of the new stuff I'll be talking about is from that paper, but I'll also be introducing some extra stuff towards the end as well. But to start off, I just want to talk about continuous variable measurement-based error correction. Sorry, measurement-based quantum computing. And so I'll kind of go through this a little bit light on the detail just to kind of get everyone up to speed. But essentially, the idea of this is to start with a resource called a cluster state. So a cluster state, which this is an example of. This is a canonical cluster state. So each node is a zero momentum state, and it's connected via CZ gates. And so this, the idea of a cluster state like this is that you'll input an input state, and by measuring each node of the cluster and choosing your measurement basis as you go along, you teleport the input state throughout the cluster and perform operations on it as you go. So a big part of this has to do with teleportation. So I'm going to take a brief moment to talk about teleportation in the context of this quantum circuit. Now, brief note, this quantum circuit goes from right to left. A common way of representing these circuits is the opposite. The reason we like to do this is because states are represented as kets, measurements are represented as bras. So this is a momentum measurement, and the measurement outcome is M. And it's nice because this maps one-to-one to direct notation. You don't have to change the ordering at all. So a measurement acting on a state is an inner product, which is nice. And hopefully, as I keep going, you'll see those benefits show up in the things I show you. But basically, I have this circuit as an input state. It's being measured in some basis, and that teleports the input state through this ancilla to the output. And that teleportation has some operation, which is called a Krauss operator, or I'll just call it a K, that depends on the measurement outcome and on this degree of freedom, which is the ancilla state's degree of freedom. Typically, like with the cluster state I just showed you, those are just zero momentum states. But the reason I put this in here is just to show you that it doesn't have to be. That's one choice that is made. I'll also introduce another degree of freedom here, and that is the measurement angle. So this has gone from just a momentum measurement to a rotated momentum measurement. And that theta is just the homodyne angle you choose to measure the cluster state in. And here's a face-based cartoon where you've got a squeeze state here. If you measured on the axis, you could measure position or momentum, but you could measure off axis, and that is defined by angle theta. And that's this angle that we're talking about here. And so that introduces another degree of freedom into the Krauss operator, this angle. And so as you measure the cluster state, you choose the measurement angle, and that changes what operation is performed on the input state. So just in a flash, what teleportation is. So that's the big point of these cluster states. You choose your measurement angle, teleport your state through, and your measurement angle I guess causes a certain operation, a desired operation. So canonically speaking, with this cluster state, you require 4 measurements to do a 1-mode gate, or this is also a 2-mode gate, where you entangle 2 different wires by measuring these nodes, and then you continue on your measurements along the way. And so I guess one problem, well, not problem, but one thing about this is that these are continuous variables. Nothing in here is kind of discrete variable at all. And I've not talked about any notion of logical zeros or ones or anything like that. So all this is CV, as the name suggests, continuous variable. So we need a way to define a qubit in our continuous variable systems. And this Gottesman-Kintaev Press School, this paper in 2001, encoding a qubit in an oscillator is I mean, you probably will have heard GKP states, that term being thrown around somewhere. But this is one way of encoding a qubit into a CV system. So here I've got the position wave function of a 0 state in the black or a 1 state in the red. And this is a finitely squeezed GKP state. So it's I guess the important part is that if you were to measure a state like this, the measurement outcome gives you information about what state you have. So you can see that the 0 state has support on even multiples of square root of pi, but the 1 state has support on odd multiples of square root of pi. So that helps you distinguish between the states, but it also means that a shift by the square root of pi changes 0 to 1. And so essentially, I'm not going to go through all the details, but the gates that you can, Clifford gates, are all defined with respect to this GKP encoding, or can be defined with respect to the GKP encoding. I'll quickly show you the wave function. The way we represent these is by a SHA function, which is, and this is an ideal one. So this is a comb of delta functions. And to make it approximate, you just damp it by a Gaussian out the front, so that lowers the amplitude as you go away from 0, but it also gives width to those peaks. But this is an ideal case. Another state of interest, which I'll just briefly mention here because I'm going to bring it up again later, is this what we call a Q0 state, also sometimes called a sensor state. And it's another SHA function, but the spacing is the square root of 2 pi instead, in both position and momentum. And so the reason why, the unique thing about this is it has no sense of, you can't use it for operations. It's not a 0 or a 1, but it does have that GKP encoding. So you can use it to give the GKP, you can use it to give the encoding to another state. And I'll show you that later, but I'm just bringing it up now in the context of these states so you can see, I guess the key difference is that spacing between the peaks. I think that's all I have to say about the GKP encoding, except here is how you would use those GKP states on a canonical cluster state. So the idea is you have your cluster state that's been made previously. You can then take GKP states and couple them in on the top. And when you teleport your input state through, once it gets to below a GKP state, you measure the GKP state and do Steen style error correction. So you've coupled a logical state in, you measure it, and that corrects errors. Now, importantly, so let me just briefly discuss how noise builds up in these, because each of these is a squeeze momentum state that has some CV noise to it. It's not perfect. And as you teleport through, that noise gets bigger and bigger. Each teleportation adds more noise. And so if you have a GKP state teleporting through here, its fidelity to the logical state gets lower and lower as, let me go back a step, as these peaks get wider, it's easier to mistake a 0 for a 1 because the overlap gets bigger. So as it teleports through and you get to this point, you take a fresh GKP state and teleport that down onto it, which eliminates the additional noise, but it converts that CV noise into a probability of incurring a logical error, which we then use qubit error correcting codes to correct. So GKP error correction doesn't exactly, it doesn't correct logical errors. It converts CV noise into a potential for logical error. So in 2014, this paper by Nick showed that this process could successfully enact 1 and 2 mode qubit gates on a CV cluster state and correct errors that arise from the accumulated noise, as long as the cluster state's good enough quality. And what I mean by quality is that the cluster state is squeezed to a certain level. So the more squeezing, the higher quality. And so after GKP error correction converts the CV noise into a potential for logical error, then as long as there are few enough logical errors, and a qubit error correcting code can fix them. And that's what we mean by fault tolerance. So qubit error correcting codes have a fault tolerance threshold, and as long as the error rate resulting from this process is lower than that fault tolerance threshold, then the qubit error correcting code can correct any resulting errors. Yeah, so for example, in this paper, for an error rate of 10 to the minus 6, Nick found that you would need to squeeze your cluster state to 20.5 decibels. And so one of the goals of the center, I guess, is to reduce that threshold. Here in 2019, this paper, we looked at the additional anti-squeezing that comes from squeezing a thermal state down to a certain level. So we looked at, that additional anti-squeezing, which is represented here. Does that have any effect on the performance of GKP error correction? And we found that no, it didn't. But at the same time, in that paper, we kind of said this 10 to the minus 6 is a pretty conservative error rate. So we said 10 to the minus 3 and even 1% leads to, requires 17.4 decibels of squeezing in your cluster state, or 15.6. So this is just to give you an idea of where these numbers were for the canonical cluster state. But while all this was happening, experimentalists were trying to build these cluster states as well. This experiment by Furusawa's group, they took two sources of squeeze states, separated them into temporal modes, so time binned it, and interacted them via a beam splitter to create these bell pairs. And then after a fiber delay, interacted them again, but the bell pair is now interacting with its neighbor. So instead of undoing the entanglement, we get this more complicated entanglement structure. I don't want to dwell too much on what this graph means, only to say that this graph is a representation of the entanglement of the state, and the different colors represent a different weighting of that entanglement. And the main point I want to make here is that this is big. So this is 10,000 modes long, and so this is I guess this is a single mode cluster state. So it's equivalent to that one line of nodes. And later they made it even bigger, to up to 1 million modes. And this is with this cluster state is about 4 to 5 decibels of squeezing, which for the 1 million mode one is an improvement. It went from, I think, 2 to 3 decibels to 4 to 5 decibels. So just to give you an idea of what kind of squeezing level these are able to achieve at the moment. And I should say, this isn't the only group to have done this. This is just the one I'm highlighting here. Here's just a quick example of two-dimensional cluster states as well that have been made. These are two different groups making kind of a similar setup. And one thing I want to, actually no, sorry, that'll come later. So that's to tell you what experimentally these things are at. But I will, make this comparison between the canonical and this experimental cluster state. They are not the same, and I think it's evident just by looking at them. But this paper in 2014 by Ralph Alexander looked at these cluster states that were being made, and asked how we could use them for the quantum computation that had been kind of defined with this canonical cluster state. And one idea was to measure each of the top nodes in position, and a position measurement on a node like that deletes the node and all of its connections. So that would reduce this whole thing down to just this one wire at the bottom, which is much more similar to this. However, that also amplifies the noise. It's basically a waste of resources doing that. And so instead, they devised a way to to group these pairs of nodes into what are called macro nodes. And you get something that looks a little bit like this, much more similar to that, but that's not really the point. The point is that they showed how a measurement across these two modes teleports an input state from one to the other and enacts a gate. And that gate depends on the measurement angles you chose. So the kind of framework of measurement-based quantum computing maps across to this to these physical cluster states as well. Now, the other difference between these I'll point out is I've left these nodes of error correction here because error correction hadn't been done on these macro nodes yet. And so part of this work is to say, okay, how do you do error correction with this physical resource that we have? Now, at this point, I'll point out that this is a one-dimensional cluster state, even though there's, even though it's like a two-dimensional grid, it's a one-dimensional cluster state. But all the two-dimensional cluster states that have been made, those ones I was showing you earlier, they all reduce down to the one-dimensional case. So everything I talk about in terms of this macronode wire can be mapped towards those high-dimensional cluster states as well. Yeah, so error correction on the macronode wire, that's the question. We looked at this experiment that I showed you earlier and said, well, we could take those Q0 states, those GKP states I was describing earlier, and we could place them in place of one of these temporal modes at the beginning of the experiment and just let them propagate through. And we could do it either with one beam or the other beam, or we could put one on both. And there's just a reminder of what that Q0 state looks like. It's a shaft, its wave function is a shaft function with square root of 2 pi spacing. So the question is, doing these things, does that do error correction? And if it does, what does that mean? But in order to answer this question, we looked at a more general case, saying, okay, we could put any states in there, like I was describing earlier with teleportation. The choice of ancilla state is a choice, and we could put any state here. And if we do, the circuit for measuring these two nodes and teleporting a state from there over to there looks like this. So we have an input, which would be here in this case. We have two ancillas, which are here and here. You can see they're connected by a beam splitter. And we have our measurements on these two nodes. So the output is here. And just quickly, these arrows are beam splitters as well. So the part of interest here is this this arbitrary two-mode ancilla state. And just like in that earlier circuit for teleportation I showed you, when you teleport, when you make these measurements, you teleport your input through here to the output. And that will enact some gate, and the gate is dependent on these states and these angles. So I'm gonna take a few steps back in order to work up to what this means, what this is. So this is an EPR state. This is a standard representation of an EPR state. We have a continuous variable controlled NOT gate, or a CX gate, acting on position and momentum eigenstates. And that gives you an EPR state, which in a circuit we represent as this, this angled wire connecting the two, and an identity gate. Now I've left this identity gate here to emphasize that what we call the teleported gate is the gate that acts on your input after teleporting through the two-mode state. So if it's an EPR state, you teleport through a two-mode state by measuring the top two wires. You're enacting an identity gate on your state, so you're not doing anything. And this is normalization, just ignore that. So let's make this a little bit more complicated. We actually have a beam splitter acting on these two states. And what does that mean? So we can simplify this using this decomposition of a beam splitter, which is a C0 gate, some squeezing, and another C0 gate. This open dot here just means that it's weighted by -1 instead of 1. But we just put this in place of the beam splitter and then look more closely at this this circuit element here. The exponential that represents this controlled X gate is e to the I P1 tensor Q2. Now note the eigenvalues of P1 and Q2 are right there, T and S. So we can replace those eigenvalues in the exponential and it just becomes phase. So essentially it goes away. We remember that it's there, but it doesn't affect the rest of this. We then act these squeezing on here and here, which just multiplies the eigenvalue by √2. And then we take out the shifts. So they come out of here. Now, the important part is this Z is a function of position operator. So it commutes with this position operator. X is a function of momentum. It commutes with this momentum operator. And then this controlled X gate acts on these two using this identity, identical, to give us an EPR state here with these two displacements. But we can take it one step further to simplify this by introducing a pretty cool technique that can be done with these EPR states. We call it bouncing. So any operator acting on an EPR state can bounce down to the other wire by having a transpose. Now that transpose is with respect to the basis in which the maximally entangled state is perfectly correlated. So for an EPR state, that's position. And that leads to some nice bouncing rules. So the transpose of the position operator with respect to the position basis just leads to position, but for momentum, it leads to negative momentum. And most of the operators can be bounced using these simple rules. Some become more complicated, but these displacements, for example, this Z operator, Q bounces down to Q, and so it just goes like this. If X was bouncing to the top, this would become X dagger up here. It's as simple as that. So taking this back to here, I just want to remind you of this phase we introduced earlier before showing you this displacement operator is some phase, just like what I showed you a second ago, with this X and with this Z. And conveniently, it works out that this is an EPR state with a displacement down here. All right, so now this identity is the teleported gate for an EPR state. This displacement is now the teleported gate for this other state. And there's not much difference between these two, but what we're really interested in is what is the teleported gate for this arbitrary two-mode state. And so to work that out, we'll just have a look at that element and we can write it down. Like I was saying before, our right to left notation allows us to just write this down exactly as it appears. So a beam splitter with a psi and a phi. Excuse me. We just express psi and phi like this. I'm going to kind of, this derivation is short. I'm not going to dwell on it too long, but I will show it to you. Psi and phi just substituted into this equation like this. Now the beam splitter doesn't act on the wave functions or anything. It just goes straight over to the kets. And now if you're paying attention in the last slide, you'll see that this is a beam splitter with a momentum eigenstate and a position eigenstate. And that is a displacement acting on EPR state. So we can just use that directly. And then we can rewrite this in terms of alpha, where S is alpha real and T is alpha imaginary. We just get this integral. And that is what we call the A operator, or our teleported gate for this arbitrary state. So we have three circuit identities. Now, the really good thing about this A operator is that it's general. Obviously, that's a good thing. But that means we can take the wave function for any set of Gaussian or non-Gaussian states here and use A to figure out what effect that would have on an input state teleporting through them. But it's even more versatile than that. We can even use it to figure out what these measurements do. So this is a measurement, but if we take the dagger of it, we imagine that they're states and use their wave functions in this A operator, we find that we have some operator that depends on theta A and theta B and a displacement. And I will show you what this V is exactly, but right now I'll just point out that this is kind of in the spirit of teleportation based, or sorry, measurement based quantum computing, in that you choose a measurement, you choose your measurement angles or your measurement basis, and it enacts some gate based on that basis. And so your measurement angles plug directly into this equation. There's no equation here, but into the equation, and controls which gate gets put here in the circuit. In any case, I'm going to use those bottom two circuits, those bottom two circuit identities here and here, to simplify this circuit. So this is what I showed you earlier. I won't jump back to it, it'll take too long, but this circuit represents one macronode measurement with arbitrary ancillas. And by just swapping out those two circuit elements, it simplifies to this. And the reason this is good is because if you pull that output and that input toward, these EPR states hit each other and become one wire. And so we just have an input state being hit by a couple of gates, and that's it. And so we can just directly write off what our Krauss operator is in the exact same order as it appears in the circuit. So our Krauss operator is this V, a displacement, and this A. Now let's look closer at the V now. This V is not new right now, but the derivation that the derivation resulting from what I showed you is new. And it's a rotation, a squeeze, and a rotation. And this can enact two of these, so two V's or two macronode measurements can enact any Gaussian unitary gate. And that's, I guess that's been the basis of a lot of macronode based circuits, cluster states and measurement based quantum computation using them. So this V gate is pretty standard, but that's what it looks like, just to give you an idea. And again, it depends on the measurement angles, theta A and theta B. And the A operator is here. You've seen that plenty of times, but here it is again. Just to remind you, that comes from choosing what wave functions, what states you want to put in here. You use their wave functions to work out what effect that has on your input state. And so, yeah, but back to the point, we were using this to figure out what error correction looked like on these macronode states. And I guess these are just the result. I mean, if you have a Q0 state in one position, then you get half of error correction, and depending on which spot you have it in, tells you which quadrature you're going to correct. But if you have it in both, you get the full GKP projectile, which corrects both position and momentum. And what I'll do is I'll just quickly show you how you would use the A operator to come to this result. It doesn't take long in this case, but start with the A operator and using the wave functions for the Q0 state, which I showed you earlier, that is this SHA with the spacing square root of 2 pi, pop them in there. And then again, decomposing or representing the displacement in this way. Now, one problem that arises here, and this kind of tells you about the choice of using a Q0 state in this place. This e to the I alpha real, alpha imaginary mixes those two integrals together, which makes it a little bit more complicated. But if we look at the allowed values of alpha real and alpha imaginary, that is the square root of 2 pi only, well, and integer multiples of that. I've ignored the integer part for this because it's unnecessary, but it just equals 1. And so the choice of Q0 states here allows us to make this simplification. So it allows us to just have two separate integrals where the position and momentum shifts here act as Fourier kernels for a Fourier transform on these SHA functions. A Fourier transform of SHA function is just another SHA function with different spacing. So we get this, this operator here. And this is just the full GKP error, the full GKP projector in terms of SHA functions. Yeah, so I mean, that's kind of like the crux of error correction. But I think the important point of the paper is really this A operator and the formalism that comes along with it. The bouncing and the representing circuits in terms of EPR states, and being able to have these arbitrary states in for your ancillas. And again, emphasizing that that's Gaussian and non-Gaussian states that can be put there. So that's kind of it for everything that was in that paper. What I'm going to do now is I'm going to kind of continue on the story with work that I'm doing now, and a paper that's in preparation. Hopefully, will be out there soon. But just kind of reminding you, in canonical cluster states, for these error rates, to achieve these error rates, required squeezing of 20.5 decibels, or for 10 to the negative 6, 24.5 decibels, 10 to the negative 3, 17.4 decibels, and 1%, 15.6 decibels. So that was for canonical cluster states. And now that we've defined GKP error correction on macronodes, we can begin to make similar statements about how error correction performs on these macronode-based cluster states. And so that's what we're doing now, along with streamlining the measurement process to make some improvements to measurement-based error correction on macronode-based cluster states. And that, I'll just, spoiler alert, that leads to, I'm going to talk a little bit more about how we streamline the measurement process, but I do want to just compare directly our preliminary results for 10 to the minus 6, which I've included, even though it's very conservative. I've just included it for comparison. You need about 16.9 decibels of squeezing on your cluster state. 10 to the minus 3 is about 13.7 decibels, and 1% is about 12 decibels of squeezing. So you can see an improvement from previous results sent out by the center. And so, I mean, this is really one of the big goals of the center, to reduce these squeezing thresholds, which is why I'm highlighting it here. But let me briefly tell you some of the other improvements that we've made to this process. So first of all, Gaussian unitaries that implement the Clifford group on GKP encoded states. So for universality, you need to be able to implement the Clifford group. And so these CV unitary gates are able to do that. The identity gate, Fourier transform, the shear, and the control Z gate. They map to the identity, the Hadamard phase, and the control Z gate. Now, typically, as I've mentioned earlier, we know that any Gaussian unitary gate can be implemented with 2 V gates. So that's 2 measurement steps along a macronode wire. And most macronode-based cluster states and work around them has worked under the assumption of 2 measurement steps per single gate. But the important point that that we're pointing out now is that although any Gaussian unitary gate can be implemented by 2 Vs, we only need these unitaries. And all other Gaussian unitaries can be implemented by some combination of these. And so with this 1 V gate, we show that you can implement the identity, the Fourier transform, and the shear. So these are single mode gates. The CZ I'll talk about in a minute. And so that is a big improvement. We now only need 1 macronode step to implement one of these gates. And that means that that's going through half the nodes, collecting half the noise, which makes error correction easier and makes error correction succeed more often. So that directly results in a reduction of those thresholds. So what about the 2-mode case? Well, what I'm showing you here is a circuit for the quad rail lattice, 2 modes in a 2 macronodes in a quad rail lattice. And before I go on, I just want to kind of invite you to use your imagination and ignore those red beam splitters there. What you then have is a beam splitter on these rotated measurements and a beam splitter on these ancilla states. This circuit here is identical to the single macronode circuit I showed you earlier. So what we have here is two single macronode circuits that have been connected by beam splitters in this way. So, and now I'll show you a way that we can represent this that's more general and much nicer and can inform us of a few things. So first, I'll tell you, I'm not going to prove it. It can be proved using symplectic matrices, but these two red beam splitters commute with these two black ones. So we can swap their ordering. Again, multiplying the symplectic matrices together and then multiplying in the opposite way, you can compare them in and you'll see that it works. But basically these are the same. We can swap the order. And then just like I did before, we can use those circuit identities from earlier to represent the circuit in this way, which is nice because we like these EPR states. We like being able to freely move things around and explore explore other ways of representing the circuit. Then this beam splitter here can slide over to here. Nothing's in its way, can slide all the way to these EPR states, and we can bounce both ends of the beam splitter up. Now, this bounce is not as trivial as the one I showed you earlier. So for the moment, just trust me, I guess. But we can bounce it up like that, and it just daggers as it goes up. And now we can, again, from earlier, we just pulled these out and collapse the EPR states on each other. Now we have some two-mode circuit, which is much nicer to look at. I'm going to commute those displacements through, just in case you're interested. This is what the displacement looks like. So that's for A and B, and then for C and D, we would just have C and D in place there. But as I commute them through, they change slightly. Don't worry too much about that. But we have this general two-mode gate now, which is brand new, hasn't been shown before, which is in terms of the old V gate, which is nice. So we can use that to make a few statements about this two-mode gate. Firstly, if we make V equal a shear of weight 1 and a shear of weight -1 on the bottom, this is equal to a CZ gate. So what I'm telling you here is that what previously people thought you needed two steps to implement the CZ gate. I showed you a second ago that we could do single mode gates in one step. Now I'm showing you we can also do two-mode gates in one step, which is great. And we can also, this is kind of side interest, but I think is really useful. We can also disentangle our two-mode gate. So we don't actually, we can have permanent beam splitters in there, but by choosing our measurement angles, we can decide to get rid of the effect of those beam splitters and have two single mode gates instead. So if you choose two single mode gates that are the same, there are certain cases where that commutes with a beam splitter. So those cases are at least, there's probably more, but identity gates, rotations, squeezing, and shears, as long as they're identical on both wires, they can pass through the beam splitter with no effect. And then these beam splitters just cancel each other out, and you're left with those two gates on both wires, which is really good. So critically, those reduced thresholds are affected by reducing the amount of macronodes we need for a single gate, which not only reduces the thresholds because error correction is much easier after doing one error correction per gate. It's also good because it helps us to use our cluster state a little bit more efficiently, as is the point of this disentangling gate. So we can have permanent beam splitters there, and even though we have beam splitters interacting two macronodes, if we don't want to do an entangling gate there, we can choose to disentangle it rather than just delaying until we don't have any more entanglement. Yeah, so this I'll just show you as like a final thing. Those squeezing thresholds I told you about before from these graphs. The single mode gates are here, and the two mode gates. Now, just quickly, we'll highlight these two mode gates are a little bit more complicated than what I was just showing you. That's because these thresholds were calculated before we finalized that simplification. And so, but we don't expect that that will change the thresholds at all, because Fourier transforms have the same noise properties as the identity gate, for example. So that won't have any effect. But yeah, thank you for your attention, and I'm happy to take any questions.